A plate of mass M is hung on a vertical spring attached to a ceiling, which causes the spring to stretch by an amount d to a new equilibrium position, and a lump of clay of the same mass M as the plate is dropped from a height h above the plate and sticks to it. So we're going to derive several formulas in part A and express all answers in terms of M, d, h, and physical constants. So part 1, we want to get the speed with which the clay hits the plate. So we're just dropping something in a state of free fall. We've done a problem like this many times before now. You can use either free fall kinematics or conservation of energy, and I'm not going to show you the work in this one. I just expect you to be able to kind of show that on your own right now. So the final answer you get for that is that V is equal to the square root of 2gh. If you're really stuck and don't remember how to get that, go back and look at the problem with the two spheres on top of each other, the small sphere on top of the large sphere, where you drop them and it hits the floor, and then the small sphere bounces much higher after the collision. Part 2, the speed of the plate immediately after the clay strikes it. Well, this is a collision between two objects, so you want to set the initial momentum, the m1 v1 initial plus m2 v2 initial is equal to, now since they're stuck together, it'll be m1 plus m2 v final. We'll let the first term represent the clay, so that'll be m times the speed v, which is the same speed we got up here. The second term will represent the plate, which is initially not moving, so we can just say that term is 0. And that's equal to the two masses added together, m1 plus m2, which is 2m times v final. The m's cancel out on both sides, so when you solve for v final, you'll get v final is equal to v over 2. Plug in that formula for the v, and you've got your answer to part B. To part A, part 2. And then part 3 of A, the period of the resulting oscillations. So we know the period of a mass spring system formula is 2 pi times the square root of m over k. In this case, the plate and the clay are together, so it has a mass, total mass of 2m divided by the spring constant k. Now, here's an issue that a lot of people are still having on the tests. It says at the beginning that all the answers should be in terms of m, d, h, and physical constants. The only physical constants we've discussed so far in this class are little g, big G, the speed of light, which came up briefly once, the c, that was the lowercase c, and then any mathematical constants like pi. So you should not have anything else in your final answer. So if you just leave your final answer like this, it's wrong, because it has a k, and we don't know what that k is, but you cannot express the final answer with a k in it. It can only have an m, a d, and an h in it, or constants. So we need to figure out what this k is in terms of other letters. You cannot just leave your answer like this. So we need to go back to when the plate was first hung on the spring. The spring has a certain initial length, and then when the plate is hung on it, it causes that spring to stretch a little bit. And the amount of the stretch from its rest length to where it was stretched, you were told is this capital D. So if I draw a free body diagram for the plate when it's first hung on the spring, there are two forces acting on it. The downward force of gravity from the weight of the plate, and the upward force of the spring. And since the plate is not moving, I can just use Newton's first law, net force in the y direction equals 0, to say the upward forces, the spring force, is equal to the downward forces, which is just the gravitational force. The spring force equation is kx, but in this case the x is represented by the capital D, and then the gravitational force, mg, and from this simple equation, I can solve for k in terms of the other letters. So k is equal to mg over d. That's what we have to substitute into this equation. So the period is equal to 2 pi times the square root of 2m over mg over d. You're going to see that the m's cancel out, and this d, which is in the denominator of a denominator, will shift up into the numerator. So your final answer for the period is 2 pi times the square root of 2d over g. And for part 4, I put a note on Schoology that said you could skip that part because it's a little more complicated than I anticipated when I wrote the question. So, in the next part, the clay is removed from the plate, and the plate is returned to its equilibrium position on the spring. A rubber ball of the same mass m as the clay is dropped from the same height, and after a perfectly elastic collision with the plate, it's caught in midair before hitting anything else. So we want to determine if the period of oscillations in B part 1 is greater than, less than, or the same as it was in part A. So since the equation for the period was T equals 2 pi times the square root of 2m over k, that's what it was initially. Now what's happening is the mass of the thing that's oscillating is just m instead of 2m. So this 2 is no longer there. So this is the new period of oscillations. And if you plug the same k value in as before, t is equal to 2 pi times the square root of m over mg over d. The m's cancel out. Shift the d up into the numerator. And you've got t is equal to 2 pi times d over g, which when you compare it to the original equation that we had is less by a factor of the square root of 2. So because this has a lower period, it's going to oscillate a little bit faster. So in your justification, you can justify it just in terms of showing the equations like you did here, or you could justify it with an explanation just by saying that the period is proportional to the square root of the mass. Since the mass is lower, that means the period will be lower also. And you don't have to do B part 2 since that kind of depends on the answer to A part 4, which was eliminated.